let us know. Thank you.
Great, thank you so much. Thank you, Vinay, for the introduction. Thank you, Ali, for the invitation. Thank you, Divya, for the poster and all the nice work you've done in the background. I'm very happy to be here. I'm just going to start sharing my screen. And I hope you all see that. And then we can get started. So I want to talk about prototypological research towards circular construction. And to start us off, I think it's always important to basically look a little bit at the bigger scale. These are graphs of the human influence on the planet in the last 250 years. And they are scarily similar, right? So it doesn't matter if you look at population or GDP growth or fertilizer consumption or paper production or the loss of the tropical forest. All these indicators are exponential in growth, and they start really growing around the 1950s. And that's one of the reasons why we're now talking about the human epoch, right? So the introduction of the Anthropocene as a new geological time epoch, which is huge if you look at it. In other lectures, I sometimes talk about what defines a geological time scale, right? And so the last 12,000 years were determined by planetary constellations, the angle of the planet to the sun. And so now the human influence is more important than these big scale planetary systems. I think it's important to keep that in mind. And if you look at a couple of these charts in more detail, then these are graphs of the global resource extraction. And on the left side, you see the total amount. And you might say, well, this is just because we are more people on the planet now, we use more material, right? But on the right, you see the per capita consumption. And so this is actually not just due to the fact that we have an exponential population growth, that we're all using and extracting more material. And what you can see here as well is the influence of the built environment. So the magenta colored are the building materials. And it's really important for us as architects to be aware of that, right? The influence of buildings over their whole life cycle is, we extract more than 50% of all materials from the earth are extracted for buildings. More than 50% of all the waste is produced through building and construction. And 39% of the carbon emissions can be related to the built environment. And if you look at that a little more detail, then of course the carbon emissions chart is again a very similar graph, right? At 1950s, it starts picking up, it goes exponentially up. But then the important part is what happens after the now, right? And so if you look at graphs, and these are from, and I'm sure you know those, I'm preaching to the choir here, but these graphs are by Architecture 2030. And the estimate is that if we don't reduce our carbon emissions in the next 10 years by 65%, we have no way of reaching the Paris climate goals. And so the next 10 years, this is nothing considering how slow our industry is moving. Right? To significantly change the built environment in 10 years is quite a task that we have as a collective in front of us. And one potential way of doing that is to move from a linear economy to a circular economy, which talks about material cycles, the separation of technical and biological resources, and of course a shift in the energy sources that we're using to keep these cycles running. And if you wanted to define the circular economy, which is actually quite difficult because it's usually defined as the anti-thesis of a linear economy, there's no commonly accepted definition yet. but the Ellen MacArthur Foundation is phrasing it as a restorative and regenerative economy by design that keeps parts, components, and materials at their highest utility and value at all times and distinguishes between technical and biological cycles. And unfortunately, as we all know, this is still kind of the current status quo, right? At the end of a building, at the end of the use phase of a building, there's demolition, there's landfill, there's very little recycling, at least very little high-level recycling happening in the built environment. And so what we're trying to do here at Cornell right now is through the Circular Construction Lab, develop tools and develop methods that can influence this paradigm shift. And so we're looking at, on the one hand side, how can we design buildings differently, and how can we design buildings as material depots for future use? And what can we do with everything that is out there? How can we activate the potential of the built environment as an anthropogenic or as an urban mine? This includes looking at circular materials that can be reused or recycled or cultivated, what we're talking about today. This involves looking at new details, reimagining construction, and it involves looking at different types of documentations and estimating the stocks and flows in the built environment to somehow match demand and supply, which is another really important area in kind of the shift towards a circular economy in the built environment. And so when Ali asked me to speak today, he actually referenced this paper that we published in 2019, Pioneering Construction Materials through Prototypological Research. And so I thought it's important to talk a little bit about what we understand with prototypological and what actually research in architecture in our realm can be, knowing that this is a kind of graduate school and you're all dealing with these questions, similar that I'm dealing with these questions every day, and maybe hopefully we'll have an interesting discussion at the end about what research actually can be in architecture, right? But going back a little bit in history, I wanted to take a couple of excerpts from that paper to spin the story, how we define our methodology. And so in 2007, Jeremy Till, whom you might be familiar with, wrote a paper that he starts with, "There's still amazingly debate as to what constitutes research in architecture." And he then continues by basically abandoning 3 myths. And the third of these myths is that building a building is research. I'm going to read a little bit. "Certainly, from the very beginning of architecture, research has been conducted through the process of building. Trial and error in design and construction, in combination with observation and study of the built environment and connected disciplines, often led and still leads to the application of new innovations. Constantly in architecture, design and research have been understood as something closely interconnected for many centuries, neither polar opposites nor equivalent domains of activity. Rather, the relationship between the two is far more nuanced, complementary, and robust. According to Till's argument, the flaw lies in the definition of the goal. Architectural knowledge may lie in the building, but it also lies elsewhere, in the processes that leads to the building, in the representation of the building, in its use, in the theories beyond the building, and in the multiple interpretations of the building. So architecture exceeds the building as an object, just as art exceeds the painting as an object. And so he concludes that architectural research must therefore address this expanded field." A very different character, Winnie Maas from the Y Factory and MBRDV, in 2017 then encouraged the discipline through his book Copy Paste to stop suffering from its syndrome surrounding the originality. right? We always reinvent the wheel with every building. That's the goal. And the interesting part in this reasoning is that it understands the single building as part of a continuous architectural research, following Till's argument, and not as research itself. And so it also follows the definition that science, which progresses via researchers building on the work of others, right? So speaking for the architectural practice, he continues in the book, Vinnie Maas continues, why not deepen our architectural analysis? Why not be open and honest about the references we make? Why not improve on the explorations, innovations, and suggestions of other predecessors? This, of course, directly addresses the architectural profession, not necessarily architectural research, but nevertheless, it's a kind of important contribution to this debate, in my opinion. And then when you ask yourself what is actually architectural research, you can also go back to 1984, when James Snyder defined research in general as systematic inquiry directed towards the creation of knowledge. And in this context, the word systematic, I think, is essential, because it strengthens Till's argument on the one side that the building by itself may not count as research, right? Because design decisions in the architectural office, for example, are often research-based, but usually not systematic. And secondly, it also implies the need for a research methodology, right? Systematic needs a research methodology, which can be understood as a constructive framework to structure and describe the research methods. And so what we're trying to do is basically implement prototypological research as this methodology. Next to many of the accepted methods, like qualitative, quantitative, conceptual, applied, analytical, descriptive, empirical, fundamental, etc. There's this kind of the need that we're having to shift this mindset in the architectural world. We're hoping that by adding prototypological to this list, we have a better tool to address architectural research. And a little bit about the definition of what prototypological is. It's a word that is joined, I'm sure you all figured that out, by the words prototype and typology. And so a prototypology represents a full-scale application that is an experiment and proof in itself to effectively and holistically discover all connected aspects and addresses unknowns of a specific question, yet at the same time is part of a bigger and systematic test series of such different typologies with similar characteristics, yet varying parameters. This was first defined by Andreas Ruby in 2003 in this quite exciting book, the Metabolist Dictionary of Advanced Architecture. And so to use Andreas's words, just as the prototype anticipates a product yet to be developed, the prototypology represents a typological configuration in permanent state of evolution. Whereas a conventional typology defines a generic model of organization, which becomes specific through its application, the prototypology is specific from the beginning. On the other hand, it never really becomes generic as it continues to transform itself through the information it receives. And so building on Ruby's definition, the goal of such a prototypology can not be a formalistic debate, right? We're not talking about how does this building actually look like, but rather the discovery and verification of skills, information, culture, climate, material, techniques, and other soft and hard parameters within this given context. And maybe this is best explained if you look at other industries, right? So this is clearly a prototype. And no one questions the word here, right? Because we're developing a specific form, a specific setting of parameters, which then goes into industrial production. And so we're building a couple of millions of these in the factory, which are the same. I mean, you can still verify which kind of radio you want and which leather you want on the inside, but the basic setting is the same, right? And similarly, in the modernist area, we had prototypes in architecture, like this Maison Tropicale by Prouvé, which was meant really as a prototype to be built in France and then shipped and delivered to Africa as this new housing typology, but had very little to do with site-specific adaptation, for example, right? The site didn't matter, the context didn't really matter. It was a kind of almost colonial understanding of what the context is, and then this is just being delivered. And so this is clearly a prototype, but what we're, I think, all trying to do is something bigger, right? Is developing a new type of material or a new type of looking at architectural creation. And so we need a new word. And so today I wanted to lead you through one of our prototypological research streams, which has to do with mycelium. And this is just a couple of these points on the timeline that I'm gonna touch in the next couple slides. Maybe to start with, what is actually mycelium, right? Mycelium is, it can be defined as, or the image that you can use is that it's the root network of fungi. This is not correct scientifically, because actually the mycelium is the organism. And what we understand as a mushroom, if you go in the shop and you buy an oyster mushroom, like the one you see here, that is just the fruit, right? So if you wanted to compare it to an apple tree, then the mycelium would be the tree, and what we call the mushroom would be the apple. And so on the left side in this bag, you see the organism. And interestingly, this is an image from Indonesia, from basically a mushroom farm. And you see the scale of this production in the background. And all of this is a waste product at the end, right? This goes all to the compost, because this production is only interested in the mushroom itself, in the fruit. And so you see, and while you see this mycelium grow here on the screen, we can talk about the properties, right? It's an incredibly dense network of hyphae, which allow potentially to be a sort of biological glue, like an adhesive that can self-assemble through this growth process, trying to find nutrients. And it's been applied in architecture over the last 10 to 15 years in different pavilion structures and small scale applications, but never reached a kind of industrial scale, or hasn't yet reached an industrial scale in its application. But it is an incredibly exciting idea to talk about, and we're, I think, all, I just read Ali's latest paper yesterday. I think we're all working towards the implementation of this material in one way or the other. And so what we've done over the past couple of years, starting in 2015, is looking at mycelium from different angles. For example, here as a kind of the binder of bricks, right? The bricks you can see in the background. This is an image from the Venice Biennale where we exhibited some of this research. We've looked at it in the teaching environment. These are images from Germany, from the Karlsruhe Institute of Technology, where we used mycelium in the classroom to grow little art objects and for example, a lamp like this. This takes 2 weeks to grow, and you have a little design object that you can take home. But then, of course, you also want to look at kind of a more scientific approach. What are the parameters that is needs for growth? What are the temperature, the humidity, the light, and all the other important aspects of such a growth process that you want to be able to control very carefully to then reach a specific material that is tuned to a application that you want to use it in. These couple images from this Venice Biennale exhibition, because for us, basically all of these steps are prototypologies in the process, where we always look at one of these aspects, one of these parameters specifically, and try to understand that and tune that the material to that. And so here we really looked at the material in its ability to form a brick, and the question if this brick can, for example, be joined through mycelium. When do you stop the process? Another really important question to look at. In all of this, of course, always keeping in mind that we're looking at it from an architectural perspective, and so the strength of the material as a building material and not as a design object takes prevalence, and we've done a lot of tests for structural, tensile, and compression, and all the other parameters that are important, always changing the recipes, looking at these in different scales, developing new tools, building our own little tools to change those processes and influence the whole process. Probably the most known prototypology in the series is our contribution to the Seoul Biennale in 2017. And that had a different scale, right? So we couldn't do this in the lab anymore, making little bricks like I just showed you before, but we basically outsourced part of the production to a farm in Indonesia. And here you can see the production line of the raw material, which then basically leads to the making of two different types of like foot-sized bricks. And here you can see these bricks. And then we assemble those in Seoul into what we call the microtree. And this was the first time mycelium was used structurally. So this structure actually carries the load of the roof. It's not just self-bearing, but it's load-bearing. And the important aspect here is that we worked together with the Block Research Group from the ETH Zürich to make this possible, because we realized that the engineering part is as important as the material discovery, right? So in this form, which is basically an inverted shell, an inverted vault through this tree structure, right? You only have compression forces. There are no tension forces, there are no bending forces in this whole structure. And something that the mycelium composite can actually do quite well is take compression, but what it really can't do is tension. And if you pull on that, it's really brittle. It just disintegrates. At least if you apply kind of architectural forces to it. And so it was really important to not only develop the material, but develop the right form, the language of the pavilion to match the specifics of the material that we had at that time. And these are just images from that exhibition. And what you of course also see is the incredible quality of that surface, right? There's none of these are the same, right? This is a growth process, and so it leaves its marks on the material. There's a little movie about this, which I'm just gonna talk over to explain what I just mentioned. The first part of that is the kind of structural engineering. What you see here is a method that was not necessarily developed, but probably made applicable by the Block Research Group by basically visually representing those force lines in these diagrams to calculate through graphics. So graphic statics is what it's called. And so all of the forces in these diagrams are kind of represented directly in the right scale in these diagrams, and then were used to directly inform the form finding process of that tree. And so with that information, and of course this is not a linear process as it's just explained in the video, but this kind of constant back and forth. But then you see how then with this information, this tree was produced, right? We used agricultural waste products from Indonesia as a source, and then grew oyster mushroom strains in that to then in the end create basically two different types of bricks, as I mentioned before, the knots and then the straight elements, and the knots always manage to divert the forces into three different directions. And they were grown under semi-clean conditions, which still surprises us that this worked, and then shipped to Seoul, where we then assembled the whole thing quite quickly. There's the benefit of the whole structure is that there's not a single kind of wet connection. It's all just basically a big three-dimensional puzzle, because part of the mold already has these dowels in it, and so you just put it together. There are no permanent connections. There's nothing else. It's just under compression. So it's also quite wobbly until you then load the whole structure. But once the load is applied, it was quite a stable installation. But following that methodology that I explained in the beginning, of course, this is part to be seen as one part of a bigger research stream. And so we continued that in the next iteration of this idea for an exhibition in Berlin. This is part of the permanent exhibition of the Futurium in Berlin, a smaller version. And what we really wanted to look at here was not the load-bearing capacities, but if we could replace these little triangles that we had in the Seoul exhibition, which at that point were bamboo composites from our lab, we could replace those with mycelium as well. And so in the second iteration, then these triangles were made out of mycelium composites as well. This is pure sawdust and mycelium. And by now, this is something we call mycoboard. It's basically a replacement for MDF or OSB boards, but fully biodegradable and fully circular, because it only contains biological materials, and it's grown in the lab. And of course, there again, we do all the lab work, all the testing, etc. in the background. To end this kind of series of prototypologies, I wanted to talk a little bit about the urban mining and recycling unit, which is the building that you see in the middle, or the part of the building that you see in the middle of the screen. The bigger structure is the so-called nest at the EMPA in Switzerland. The EMPA is basically the started as the material testing agency of the Swiss government, but by now as part of the ETH domain, and really a research laboratory that talks about materials. And so they have this fantastic structure with 15, let's say, parking spots, where you can plug in full-scale research units into this building. And they asked us if we wanted to build one of those units to prove some of the ideas we published in our 2014 book, Building from Waste. And so the academic brief of that building was that that everything that goes in has to also be able to returned into their material cycles. So nothing could go to waste. And so we built that and opened this building in 2018. And the reason why it is part of this series is that it's the wall insulation is made out of mycelium in this building. And so this is a kind of grown insulation that is fixed only in place with these holders. And can be fully composted at the end of the life cycle. But I want to talk a little bit about the unit itself. It's meant to be no, it's not only meant to, it is the home for 2 PhD students of the EMPA. So you can live there for a semester. And it's a kind of residential unit with 2 bedrooms, 1 shared kind of community room, bathrooms, everything you need as a student. But of course, the big important aspect for us was to get these material cycles closed, right? And so there are 3 cycles in this building that we can talk about. There's the technical cycle of elements that are being recycled, high quality recycling. There's the biological cycle, which is a much bigger metabolism, right? So you can take a timber piece and turn it into a mushroom insulation, and then it can grow rice at the end. So the rearrangement of molecules in the biological metabolism is a much bigger metabolism than talking about technical nutrients on the left. And then there's a very small and direct cycle of reused elements. And the whole building is assembled from 7 modules. The modular construction is important in this aspect because we really wanted to have the highest possible control on those material cycles. And so if you take those questions away from the construction side towards a prefabricated and high controlled, high quality prefabrication process, you have a much better control over, for example, offcuts or byproducts and all the other potential waste streams that are part of our construction industry. And then, of course, it's designed for disassembly. So on the right side, you can see how you take this whole building apart again, and which materials are going into what stream. All of the modules stand on rails. So basically they're lifted in by 2 cranes. We had a construction site of 1 day because they're all prefabricated and ready to go. And so they basically just roll into their final location and then screw down with 2 screws. And the benefit of that is if you want to take it out again, you loosen those 2 screws and you roll the whole module out again. And so the deconstruction is a very simple plan, and it's just basically reversing the construction process. Maybe 2 little aspects of that building. One is we wanted to check if we can build a mortar-free brick wall out of waste. And so the brick that we used is it's called waste-based brick. It's made by a company, Stone Cycling, in the Netherlands, and is made out of mineral demolition waste. And with them, we developed a new stone that is specific to the urban mining and recycling unit, which is a kind of Lego system of tongue and groove. But then it also has these 3 holes in there where we added a kind of metal grid to post-tension the whole wall. And in that case, then create a kind of structural integrity of a system, but allow, once you loosen those bolts at the top and the bottom, of course, allowed for the replacement of these stones, or their use, direct reuse in some other location without having to get rid of mortar or plaster or any other problems that common brick walls have at the moment. A look into the bathrooms. These are made out of, on the left, you can see a glass, recycled glass. On the right, you see high density polyethylene walls. And the important part here is, on the one hand side, the question, how do you build a waterproof a bathroom without any permanent connections, right? How do you build a reversible system without silicones, without glues, without tile blasters, etc. And so all of this is just dry gasket connections, just pressed connections, and so far, 4 years running, we have not a single leak in this. So this is possible, but then the other aspect that I find personally really important is the aesthetic value of these materials. So you can still see the history, and it adds a completely different aesthetic, which doesn't look shabby chic, but tells a story of the circular economy. And so in the glass, you can see these glass shards, or in the plastic, you can see these pieces of plastic still in there. But this material now has been renamed as the Dübendorfer Marmor, which, if we translate it, is kind of the marble of Dübendorf, and Dübendorf is the location of this building. And so suddenly this plastic is lifted to the value of a noble stone, which I find quite interesting. I mean, this is nothing we had no control over this. This is something that then the users and visitors of this unit somehow adopted. We looked at new types of applications. For example, we couldn't find any faucets on the market that were suitable for the high level of requirements we had in that unit. None of the faucets were recyclable because they combine 3, 4, 5 metals and plastics on the inside with press fits that you can't take apart anymore. So we managed to 3D print our own faucets out of a mono material, out of stainless steel, or we reinvented the way companies are building heating and cooling panels so that they are all disassemblable. In this case, the reinvention is simply take a screw instead of glue, right? Sometimes it's an easy solution, but convincing the company to do that took months. And so there's a lot of talking involved, convincing involved in our in this shift of perspective as well. All of the media, the cables, the pipes, the water, plumbing, all of this is circular, monomaterial, disassemblable, only screw connections. And then we introduced a couple of new business models. So for example, if you have a fully recyclable material, in this case, a carpet developed by Deso, it's kind of counterproductive to sell that product, right? So you need new business models attached to that. And so these carpets are only rented, only leased, adding the safety or security for the company that in 8 years, they will get this and this amount of raw material back into the loop, right? And making them independent from volatile resource markets, etc. And then the last part that I mentioned at the very beginning is documentation. So we have a kind of physical library of all the materials used in the building. We have a digital version of that with all the specifications. And then, of course, we worked on material passports and building passports for this structure and documented all of this. In this case, the example is Madaster, which is a Dutch foundation that is very influential in Europe at the moment to develop material passports. And so you can see which material is where in the building, in what quantities, but it also allows the calculation of what they call the circularity indicator, where we reached the highest score so far. But I think the important part is not, is it now 96 or 94 or 90%? That doesn't really matter. The question is, how do you document these materials and how do you make sure to integrate them back into the loop? And so for that, you need that matching of demand and supply that I talked about in the introduction. And then a little bit of advertisement. If you want to know more, these are the 3 books. The last one, it's just coming out in April. Unfortunately, in its first edition, only in German, which I don't know if any of you can read that, but we're working on the translation. And with that, I'm looking forward to some questions.
Dear Felix, thank you very much for this amazing lecture. Like, I think so for the participants, you can use the chat to type in your questions, or we can also unmute you so you can ask your questions directly.
I did unmute everyone, so we can let everyone to start talking and asking their questions. And if they are not okay with talking, they can send their questions to you and I, and you can read them.
Yeah, so one of the participants, Julio, actually sent me a question through WhatsApp because he will have to leave. So what Julio is asking is, so let me piece together different parts, different texts that he sent. So based on the Maison Tropicale that you showed, you mentioned that the project failed because it was not, it didn't really take into consideration the context. It was, and you mentioned that it's more like almost colonial. So the question that Julio is asking is, how does the projects that you do target the context for which they are being, like the material for which they are being developed, and how does the context inform the research process in your lab? So this is a question, and let me see. Yeah.
It's a good question and an attentive question. You have to be really careful what you say. What I meant with the Maison Tropicale is that it is in its basic idea a prototype. So Prové never imagined that this building would look much different depending on where it is deployed, because it was optimized for the industrial production and for the shipment. So the important factor in the design was, how does it fit into a container? Like, what are the dimensions of the pieces? How do I get it there? And so it very much comes from the analysis of the production process, and not much other than climate, which of course played a big role in the development of these louvers, etc. The social context or the really local context of the site didn't play much a role in the design process. In our case, we are looking at this much more from a material development perspective. And so I can't really directly compare these 2 case studies, because the form itself isn't necessarily what we're working on in these typologies, but it's rather the development of a kind of technology that can be applied in different contexts and be informed by different contexts. And the beauty about Mycelium is, of course, that it is an incredible, flexible technology, right? You can grow foam and you can grow a structural material out of it. So having that flexibility in the selection of this prototypology, you can then tune it to specific and hopefully site-specific applications, right? So the carrying of the roof in Seoul or the installation of the wall in Zurich. And I'm not necessarily saying that the kind of the Swiss mentality or something influenced the design of the foam. I'm more saying that the really the specific parameters of what the material should be doing at that moment in that very specific location allows for the creation of a site-specific material. And so the comparison link misses a little bit because of the scale of the observation.
So just based on what you said, I have a question, and maybe, I'm checking the chat to see if there are any other questions. So my question is, also having done some research with Mycelium, so I know how the process goes. What were the specifications, for instance, for the Myco 3 pavilion? When you did the material test, I'm sure, you were looking for the material that bears the load, compressive load, the most, or was it the most, or were you looking for an optimal load-bearing property? So how did the material experimentation process go?
Yeah. Well, you never have only one parameter. I think that doesn't work, especially doesn't work with Mycelium, because the influence of the specific strain that you're using and the nutrient that you're using for the agricultural waste product that highly influences the qualities and specification of the final product. For example, the structural strength is never only influenced by the mycelium, right? I mean, the big part of it is it straw or is it stones, right? Because if you want a load-bearing material, the load is simply passed from aggregate to aggregate. And if you wanted to draw the comparison to cement, for example, then of course the structural strength of cement comes from the fact that you're passing the load from one stone to the next, and then you have a C curve that allows for the best optimal transmission of loads between sand and stone. And so this is something that is equally important in the mycelium research. So we had, of course, the goal to optimize for structural strength, but taken into consideration the availability of resources, in this case in Indonesia, where this whole thing was produced, the availability of skills and labor in the local context, the availability of mushroom strains, because we wanted to use a local source. And so the screening was really tuned into this local availability of resources, and then the process was an optimization process given these conditions. But then, of course, went into optimizing for strength, given also the design parameters, like the size of the brick, for example, right, which also plays a big role. How wide is that element, and how good can the mycelium still penetrate the size of the brick, and all of this. It's never one parameter. Yeah, no,
there even and especially in this case, there are maybe too many parameters. The geometry itself is a big parameter influencing the outcome. So does the audience have any questions? Because I can keep going, but I'm just looking to see if
I have a conversation here.
Yeah. Let me see. There's Kim. Okay. Nope.
Okay, may I ask a question?
Good
night.
Jose, please go ahead.
Yeah, I just want to thank Felix for this wonderful lecture. Very impressive word. I enjoyed it very, very much. And I think we got lots of inspiration from what you showed us today. That's very interesting. And I hope we can actually welcome you in person at Penn State at some point, since you are not so far away. It would be wonderful to have a visit from you.
Yeah, that would be great. Thank you so much.
Hopefully, when we have a normal life, when we go back to a normal life, it would be great to have you in person here. Ali, you said you had a question?
Yeah, Felix showed us a diagram from the different works that they've done with Mycelium for the prototypological research that they do. But I want to ask if it's possible for anyone to use the works of others in a diagram like this to put all of these works together and base their research on top of the works that are done by others and go ahead with them.
Yeah,
this is about the outsourcing of the knowledge.
Yeah, no, I think this is basically what I'm calling for also, because this is this big difference between how architects behave, right? Everyone builds its own original, right? And on the other side, our understanding of an academic that by definition always builds on the work of others, right? I mean, if you write a paper, you cite 10 pieces of work that have been done before you to show, well, this is the status quo. And then I'm building on top of that, and I know all of the history, and so I don't reinvent the wheel. That's kind of the justification of why we do a literature review, right? And so how does the literature review and the understanding of the literature review translate into the architectural scale? And that is a very interesting question. And so I think it would be great to put all the Mycelium work into one diagram and maybe draw conclusions how they build on top of each other, or show why they don't, right? And what the problem is. I mean, one example could be that, for example, Ecovative patents all its research, right? Which I understand from an economic perspective, right? They want to make money. But then building on all of their research in insulation foams, right? That would propel the industry forward. Also, knowing why they stopped producing it would be really interesting. But so far, I couldn't find out, because there's this kind of cloak of secrecy from the economic perspective, right? And so I think it would be fantastic if we started it definitely in building material research and in academia to put all of this into context.
Yeah, even I was thinking when you were presenting, Felix, you said like you had to do a lot of experiments, testing the material, combining different parameters, exploring what the outcome would be. I'm sure everyone working with Mycelium has to go through a similar process. Like to be able to understand what the material outcomes, we also did, compression tests, tensile tests. And there's, of course, existing literature that you base your research on, but still there are lots of parameters that affect the outcome. So I was even thinking, maybe, there could be an accessible open source database where we can type in all these. And at the end of the day, you end up with some numbers. Of course, the textural qualities, the aesthetics is a different thing. But when you're looking at like mechanical strength, those are numbers. So, if there's like an open source database where you can type in these kinds of research outcomes, that could save a lot of time for everyone, but also help increase this research on, mycelium based materials.
We've just been thinking about that last week. So this is, I think,
Great. Maybe that could be something that we'd be happy to collaborate, because we also have here Mushroom Research Center at Penn State, and they have these big. They have the facilities to control humidity and temperature to enable mycelium to ease the mycelium growth. So we're collaborating with them. So it would be an interesting possible collaboration.
Yeah.
Do we have any other questions?
I believe Ray asked the question in chat.
Oh, I saw it now. Ray. Just wonder the cost of making a mushroom brick compared to a traditional brick. Any follow-up life cycle analysis or estimations on how it influences the economic aspects of building making?
Yeah, it's a good question. And it highly depends on your location, because the raw material is cheap, right? I mean, ideally you use a waste product that you get for more or less for free. The mushroom itself can be cultivated, so the initial investment isn't too high, and then you can, reuse that. The problem is the scale of the industry. You need it takes 2 to 3 weeks, at least under the current conditions, for a brick to grow. If you want to make many bricks in parallel, you just immediately need a lot of space. And then space and light and you don't need much energy because they can grow in the dark. So I mean, there's a lot of economic advantages to this, but still, it potentially favors areas in the world that have lower land prices, which actually I think is a benefit to this research, because it allows us to provide a decentralized production that can happen in locations of the world that don't necessarily need a fully industrialized process in the background. And so for us, Indonesia was a very interesting case study to grow this structure, because they actually had probably a better infrastructure to start with than we definitely would have had in Seoul. We tried that, we didn't get that kind of infrastructure there. But at that point we were in Singapore, and there was no way we do this in Singapore because we couldn't get the space and the size and the industry in the background. And so I think this actually plays very well in the narrative of the material research itself, right? That it is this decentralized technology that can be potentially grown, in basements, right, on site, and so this, this is an exciting part of that. Not really a direct answer on costs. I cannot say this brick costs, I don't know, $2, and there's too many parameters play here. In terms of life cycle analysis, there have been life cycle analysis for mushroom bricks. There's a couple of them, but not really kind of a industry standard, because there is no such thing yet as an industry. The benefits, I mean, the end of life scenario is extremely simple to calculate, right? Because there's nothing in it that prevents it from just going directly into the compost and going back into the organic metabolism, and so that per se is an extremely sustainable material, because it actually helps probably the local soil, under the condition that you don't introduce an organism from, I mean, there's a lot of biological questions that you can answer on a bigger level, and ethical questions that you can talk about, but on a purely environmental perspective, there's no problem with the material.
James, you can unmute yourself. Let me unmute you. Okay.
There we go. All right. I mean, that's exactly what I wanted to ask, was the speed of that decay. You answered my question right at the end there in terms of but I'm curious about that. Have you put some out just to rot? And what does that look like? And what does it feel like? And how long does that take for a mushroom brick to return to the soil?
Again, I mean, there are two different parts of the brick. There's the chitin, and depending on how good your kind of exterior protective layer is, I mean, the mushroom at some point starts protecting itself, right? And so some of the strength comes from basically a defense mechanism that the organism has at the outer skin. And so depending on how good that protective skin is, it takes a while to get inside, right, in rotting and decomposition. The inside falls apart quite quickly. Mm-hmm. But we also don't have a scientific experiment that could back that up. We didn't do like a really, statistical amount of letting mushroom rot on a landfill or something. We don't have those numbers. But in general, the interior part is unfortunately still quite crumbly anyways. And so it's held together by the exterior.
Which is similar to a brick. I mean, that's exactly the same case with a brick. And so because once you break that skin, that brick crumbles to sand, almost immediately. So that's exciting. Well, I'm happy to watch your bricks rot. If you want to give me a few, I'm happy to sort of watch them rot. That's kind of what I do. So
sounds good.
Very, very, very fascinating. Thank you for a beautiful talk. So thanks so much.
Thank you.
Okay, so I think we already exceeded our time for this lecture, but this was amazing. Thank you, Felix. And I'm glad that Ali, you recorded it, because there were people asking me on chat how they could share this recording with other people, how they can have access to the recording. So I'm sure you're gonna make it public, maybe.
Yeah, just send us emails. I'm putting the address in the chat. It's greet@psu.edu, and we will share the video with you in an hour. And then we are going to find a better way to share all the session with everyone that are interested in watching this great lecture in the future.
Okay, so this, I think, concludes our lecture. Thank you, everyone, for joining us and joining Ali's and Grid's organization. Thank you, Felix, for this really inspiring lecture, and hope we can have you here in person one day when we're back to normal. Okay, have a nice day. Have a nice rest of your day, everyone.
Yeah. Thank you, Benai, for being with us hosting this, and thank you, Felix, for your great lecture. We will see everybody in 2 weeks with our next talk with Zubin Khabbazi. Okay, thank you, everyone.
Bye.
Bye. Okay, thank you, Divya.
Yep. See you. Take care.
See you.